So silver medalists. It's not sure what's going to happen next year. She has to switch a grade up, and they're getting bigger, and it's full contact. And it was full contact this year, too, but it gets a little bit tough playing with the bigger boys. This is a photo from one of my favorite hiking places. And I talked last time about some glacier behavior. And, of course, glaciers were very active in carving these U-shaped valleys here and just topping the whole thing and making it so easy to walk along these ridges. But today I wanted to shift focus and just talk about rock breaking. So this is my last sort of vignette. And here's some experimental work. This is actually the same place, but the following day, looking the other direction. Sometimes the weather is not necessarily Corsican in quality. All right, so this is something we can all agree on. And this is also something we can all agree on is a consequence of that sort of behavior. Now, this is the Clapeyron equation. I showed the second-order corrections and so forth to the Clapeyron equation. I don't remember where I got these estimates from, 6 megapascals. I think that probably the hoop stress and all the rest of it should come into calculating that properly. But you can ask yourself the question, at what temperature did this thing break? Or in other words, if the fridge was broken, or the freezer was broken, and it wasn't so cold, when would this bottle break? And to get to 6 megapascals of pressure, it turns out that with this Clapeyron slope, you're looking at about 0.4 of a degree below zero. -4, oh, this never happens. Oh, sorry, delta T is minus. Okay, we're okay. Worried for a minute there. You can do a little bit better and ask, well, how much headspace could I have had and still been safe? And the answer in the literature would be 9%. I think we'd be okay with 8% because we can handle a little bit of compression. This is a terrible model that is making this go because in actual fact, carbon dioxide is very soluble, and I imagine that most of it would have dissolved by that time, and this calculation is probably wrong. But this is the kind of thing that you see all the time online from engineering websites when they talk about frost damage. They talk about the 91% of the pores being filled. We saw earlier this morning that is not necessary, not at all. They also talk about this expansion by 9%, and of course, we don't think that that's the mechanism either. But it is worth asking, why is freeze-thaw such, this process of freezing and thawing correlated so well with frost damage if we don't think that it's actually the volumetric expansion that is causing the damage? And of course, freeze-thaw cycles happen all the time. I pulled this off the web this morning. The green areas are places that are in the process of they're transitional, as it said. The blue areas are frozen. This is just an entire year, 2007, of freeze-thaw cycles. They have all kinds of visualization things at the University of Montana that talk about these things. And so only the red areas and the blue areas are places that even go through these cycles. But they do impact a lot of places where a lot of people live. And they do cause a lot of damage, both to engineered structures and, of course, to natural structures like the mountains. This has been studied in the laboratory. So in particular, this is Matsuoka's from Japan and Merton's from England. And they did these experiments in Southampton, I believe, where they took a couple of rock samples and applied freeze-thaw cycles in a couple of different ways and had this cracking behavior take place. If volumetric expansion were the driving cause of this, we would expect that cracking to be dominated by temperatures close to 0 degrees because high stresses can be generated during freezing very close to 0 degrees because of the steep Clapeyron slope and all the rest of it. There is this possibility of thermal expansion cracking. That does become more prominent with more rapid temperature changes, but I don't really know much about this, and I'm not going to talk any more about that process. Instead, I want to focus on segregated ice growth, which is liquid making its way, or quasi-liquid making its way to freezing sites. So just the analog of frost heave, but in a cohesive material rather than a cohesionless material, like I talked about earlier. So back in the early 90s, and actually before this in the 80s, Bernard Halley is a very insightful geomorphologist at University of Washington, retired now. He put together a team to look at this experimentally using a Berea sandstone, which is it's a quartz-rich sandstone. It's one of the, in rock mechanics, there are certain rocks that are sold to labs all over the world and very well characterized, and Berea sandstone is one of them. It's quite strong silica bonds at the pore scale, and the nice thing about it is you can dial it up to whatever permeability you want as a starting point, because they characterize it very well. They had it in their apparatus here, and then they had these acoustic emissions sensors, and they used tomography to figure out at what location the cracking was taking place. And this is the temperature range and the number of acoustic emissions that took place. Freezing began just a little below 0 degrees because it has small pores. So there's some Gibbs-Thompson effect depressing the freezing temperature. But by far, the most acoustic emissions took place in this intermediate temperature range centered around maybe -5 or something like that. You get it colder, and the activity is over. Nothing much happens. Bernard's student, Joe Walder, had made a model of this a few years previous to that. And if you remember from your mechanics classes, or even if you don't, it turns out that the stress near a cracked tip depends on this parameter, the stress intensity factor. And then depending on how you load, things can get different once you get far away from that cracked tip. But all solutions near the cracked tip have this limiting behavior as R goes to 0. That in this case, we're talking about the opening mode of cracks. So there's 3 modes of cracks, and we're only caring about opening cracks. And engineers have done a lot of work and showed what exactly the stress intensity factor looks like for different geometries. And it's, for a penny-shaped crack, it takes this sort of form depending upon the diameter of the crack, or the radius, rather. Now, normally when people talk about cracking, you can talk about critical cracking, or supercritical cracking, or subcritical cracking, and so forth. In their modeling work, Walder and Halley assumed that it was subcritical cracking that was promoting the growth, and all that means is that cracking begins before you reach a critical value at some lower value called a stress corrosion limit, and then the rate at which the crack can open depends on the ratio of the stress intensity factor to that stress corrosion limit. It's a common way of doing things, particularly because it does give you a rate of crack growth, which is kind of nice, and it doesn't require you to get all the way up to the critical stress intensity factor. Typically, this stress corrosion limit is found to be about a factor of 3 smaller. Now, the extension of the cracks in this model came from water movement through the fringe, which of course is driven by Darcy's law. And when you stick in the generalized Clapeyron equation, like we had on Tuesday, I guess, or Monday, or whatever day it was that I first talked, you have this dependence of Darcy flux on temperature. So there's actually, in this model, there is a limit on crack growth that has to do with the The stress intensity factor, this subcritical crack growth has a velocity dependence in it. But then there's also a limit to how quickly you can supply water. So there's those two factors. And just to make a small point, that's the crystallization pressure which is identical to what Daniel was talking about. I've often used this value instead with the density of ice appearing up top here instead of the density of water, and that gives you a slightly different number, but they're the same thing. All right, so this is the model results, not the experimental results. Model results for subcritical crack growth, and at this time in westerly granite, which is another one of these rocks that's been well characterized and gets sold all over the place. This one's from New Hampshire, I think. I'm not sure. They had a temperature gradient applied of 1/10 of a degree per millimeter, and this is the temperature on the bottom here, and the crack growth rate that's predicted for freezing after 50 hours and freezing after 100 hours, and same over here for slightly smaller cracks. And then this shows a time evolution rather than the dependence on temperature for two different crack radii at two different temperatures. And the basic take-home message is that just like in the acoustic emission data, what they anticipate is that you needed to get it cold enough for the cracks to grow. You need to generate enough stress to open up the cracks. And then as you make it colder, you're pushing harder, but it's also getting harder for water to flow up to the crack. And so you wind up with a peak in temperature and also some interesting behavior in time that comes out of these models. And it's just models here. We're not observing these cracks growing. It's not in the careful well-controlled laboratory sort of apparatus that one might like. I'm going to just briefly mention my academic sister, I suppose, Joanna, who I've never met, but her co-author is sitting in the audience here. What Joanna did in this paper, and there's another paper that precedes it, is do a really nice analysis of a single crack within a porous medium. In this case, assuming that the crack grows once it reaches the critical stress intensity factor, so a little bit more oomph is required in this model. But importantly, that means that the only thing that is limiting the rate of crack extension is water transport and heat transport, of course. This is a similarity solution for a small crack, or for a crack that is too warm to actually extend. So this is the elastic deformation that precedes crack growth. And this is in the cracking regime once you get past that. So I just wanted to mention that this kind of work has been done in a couple of different contexts. So there are good theoretical developments for analyzing the behavior of a single crack in a somewhat idealized porous medium. This is, again, that place that my opening slides were from. And you can see that there are cracks of all kinds of different sizes. There's different lithologies. There is a lot of cracked up stuff lying in the valley down here, and the temperature up here is different from the temperature down here. The water conditions are different as well. There's all kinds of differences. And in the world of geomorphology, of which I'm on the tangents of, I will say, people want to be able to describe the evolution of landscapes through processes that include frost cracking as one of the dominant causes of landform evolution at high altitudes in temperate climates, where it gets cold enough at elevation for ice to form. You cannot treat every single crack in this landscape with a model. You have to do something else. This is another example from New Zealand that T.C. Hales studied for his thesis around the time that I arrived in Oregon, although I never worked with him. But similarly here, you see the alpine fault is thrusting these mountains up to impressive heights. So there's enormous relief, lots of scree coming down the side, and it is believed that those rock falls are primarily produced by frost cracking at some stage. Bob Anderson is in Colorado, I believe was one of Bernard's early students, and is a card-carrying geomorphologist. And so he knew about Bernard's work, knew about the idea that cracking should begin at some, offset from 0 degrees, and then intensify at first, but then shut down because it gets too hard to transport the water. And he introduced this idea of a frost cracking window, which he defined as being between -3 and -8 degrees based on the earlier theoretical work from his former advisor. So he just said that this appears to be, and he may have had other evidence as well, I can't remember, it's a long time ago that I read the paper, but this appears to be sort of the window in which frost cracking takes place. These curves that look all pretty up top here are just curves of the temperature variation through a year given a mean annual temperature of, I guess in this case it looks like about -2 or so, and then an amplitude of the temperature signal that takes you from that limit up to here in the middle of summer, back down to there in the middle of winter, and all of the rest of those curves are just profiles with depth of a simple extension of a sinusoidal temperature profile. And it looks like he has some dirt up here, so he probably has a 2-layer model, and it's a little more complicated than what I've shown down here. But effectively, all this is you have your cycle going back and forth sinusoidally, and as you get down, that gets dampened by this exponential. The important parameters here, py would be the period, which is a year in this case, or possibly 6 months. And kappa is the thermal diffusivity. So that's the sort of the treatment. And I don't believe that they have latent heat included in here, but that's a detail. So if you think, like Bob Anderson wanted to say, that cracking is going to be dominated within this temperature band, then an obvious thing to do is to say that places that are within that temperature band are going to experience more frost damage. And why don't we just count up the amount of time that we spend within this frost cracking window, and we'll call that an index that will give us an indication of where we can expect frost damage to occur. So it's a very simple idea. Again, just using this simple idealized sinusoidally decaying temperature profile, we can look at what happens as the mean annual temperature changes from being very, very cold, -15 degrees Celsius, to quite warm. And all of this is done at an amplitude, I believe it was 10 degrees in this calculation. I should have written, oh, no, I didn't write it down there. I think it was 10 degrees going back and forth, winter to summer. And so these are the profiles that you get. -15 degrees, if your temperature is way down here as an annual temperature, just imagine shifting that way over, then it's only going to be in the summertime that you're going to clip into the frost cracking window at relatively shallow depths, and that gets you this black curve. So the top meter gets to have a little bit of time in the frost cracking window. If you make it a little bit warmer, then the curve gets more interesting because you're -10, you spend lots of time in the spring in this window, and maybe even a little bit in the fall, and you get that blue curve. And the other curves, the green curve is for really quite warm, 0 degrees. But the red curve is a problem, because with the red curve, you're sitting right here at a mean annual temperature of -5 degrees. And that means that when you get deep enough, that the amplitude of the annual cycle has gone below, I guess, 2 degrees in this case, and you never get warmer than -3. Then the predictions of the model are that you're spending 100% of your time in this frost cracking window, and the suggestion would be then that we would expect that if we dug down 5 meters in such environments, we would find nothing but busted up rock because it's just spent its whole life being frozen. So that's not very satisfying. And the next thing that happened was that Hales and Roaring came along and decided, you know, we're worried about water transport within this frost cracking window. And we know that water transport scales with the temperature gradient. So why don't we take the time that we're in the frost cracking window, multiply it by the temperature gradient, and use a weighted integral of time in the frost cracking window. So the units change. Now we've got degrees C years per meter. Not a very helpful unit, not super physical, but it does change the patterns a lot. And in particular, we've lost any frost damage at minus 15 degrees because even though we spent some time in the frost cracking window, the temperature gradients are so shallow at that time that we don't actually see the curve. We have some other interesting things. You know, we have these different profiles. This red curve here was the minus 5, so it does decay at depth now, which is nice. And it actually sort of turns on and then turns off and then turns on again. So it gets a little bit complicated. But it achieves a goal of giving you some indication of where damage might occur. And it has a little bit of physics in it, if not very much. Okay? Well, Bob Anderson was not to be outdone. And a few years later, he came up with his own version of this, retained the same characteristics of the previous two frost cracking indices, took time in a window, temperature gradient, and then he thought, well, I really need some liquid water around in order to break my rocks, to transport to where the rocks break. And so he introduced a weighted penalty function that had an exponential behavior that decayed to something like half a meter or so. So just, you can only break rocks if there's water somewhere, is the idea. All right, so it was at this stage that that another one of Roaring's students came to me and asked to help with a study that she was doing. I think actually she asked to help with a reviewer comment that she was dealing with. And so we started to talk about these frost cracking indices, which I knew nothing about. I did know about the first two, I suppose, but I hadn't been involved. And the question is, well, can we do something a little bit better than that? And I'm going to emphasize that it's only a little bit better, okay? We do not want to hang our hats on this, but how does the frost damage actually depend upon environmental factors and material properties? I mean, material properties presumably go into determining that frost cracking window, and possibly you could work a permeability into the Anderson's version with the penalty function or something. But they weren't explicit. It wasn't clear what goes in, where, and how it all behaves, and can we apply it to different locations with different rock types. So this is what we did. As I said, it's only a little better. We made the hypothesis that frost damage is going to be more in locations with ice growth when it's cold enough to crack. So that's the starting point. So we'll start from the idea that, as Joanna showed, you can deform rock at warm temperatures elastically, but you have to get it cold enough to actually crack the rocks. And we only care about the cracking of the rocks. If it just is elastic deformation and recovers, we don't count that. So then the question is, just with mass balance, how does porosity change when it's cold enough to crack? Because some of that porosity change will be inelastic. Not all of it, but some of it. So here's our assumptions. We're going to assume that cracking begins once we reach the critical stress intensity factor. And we're going to idealize things an awful lot by saying there's only one crack. Only one crack type, one crack orientation. So that cracks happen when the ice pressure reaches some cracking pressure. And the cracking pressure, we can throw in the penny-shaped cracks and the stress intensity factor, the critical stress intensity factor for a particular rock, and choose a crack size and so forth. So we can sort of tune this according to what we think the environment requires. Mass balance, we're going to only deal with cases that are fully saturated. I'm fully in agreement that frost damage happens in unsaturated conditions as well, but fully saturated conditions are much easier, and a lot of the geologic world is fully saturated, at least in the wintertime. So then you have changes, and we're going to neglect the difference in densities between ice and water because that's just a detail that we don't need to deal with. So then porosity changes take place, as Gray showed yesterday, as the divergence of the Darcy flux, and I think we'll hear more about that tomorrow. The Darcy flux in this case is just the ratio of the permeability to the viscosity times the pressure gradient, which here is the water pressure gradient. Now, because we're going to be thinking about conditions that take place when it's quite cold, the permeability is going to be a function of temperature. So we just expand that out here, and there's our equation. We're going to say that the generalized Clapeyron equation works, but with the ice pressure pinned to this cracking pressure because the cracks are buffering that pressure. And we'll say that pressure is constant within the zone where cracking is taking place. And if that's the case, then the pressure gradient of the liquid is just proportional to the temperature gradient through this thing that is sometimes called the crystallization pressure. So if I do that, I can get rid of all the grad p's, and I wind up with a grad t squared and a del squared t in my equations. Next, I'm going to do something that some might object to. I'm going to ignore latent heat, because cracking only takes place once the pressure gets high enough to propagate the cracks, and by that time, most of the water is already frozen. And so I'm going to just say that let's forget about it, in which case I can substitute for the Laplacian of temperature by the time derivative of temperature with the thermal diffusivity showing up down here. And then just to cap everything off for the moment, I'm going to assume that we've got periodic annual thermal forcing, just meaning that if we start at what is it? It's May the something, 3rd, 4th? Okay, so May the 4th next year, mark my words, it will be exactly the same temperature as it is now. Okay, so that's the idea. And if you do that, and I just integrate the change in porosity over time, I get to throw out that term because it doesn't matter what the temperature signal is. I'm going to go back to the same temperature, and integrating over time, it doesn't matter. So I'm just left with this expression, which is sort of looking like time within the frost cracking window, except it's a little bit different in that I've got a permeability change with temperature in there. And rather than everyone else wanting to have a temperature gradient, I'm getting to square mine. So I win. So I make it a little bit more complicated. So what does that predict? We're back to our frost cracking indices. And these are my curves. So same basic story, you know, the winter time, or excuse me, the coldest locations get warm enough just in the fall. The other locations do interesting things. There's a couple of things I wanted to point out here. This is the expression that we have. I didn't mention it, but I stuck, for my permeability function, I made it a power law in temperature, is what I did. So that's where this alpha comes from, the power law in temperature. There's a single parameter that comes out here that is dependent on a bunch of physical things. This delta Tc is the temperature at which I start to crack rocks. K sub c is the permeability at that temperature. Alpha comes from the exponent in the permeability law, and the rest of these things are physical constants. One thing that I did manage to get away from is that whereas all those other indices had to worry about some window in which frost cracking takes place, because I stick the permeability in here, I naturally lose my ability to transport water once it gets cold enough. I only need to pick one of these temperatures. I don't pick a lower temperature. It's going to naturally come out of the solution. So that's something. And then there's a couple of other things. One thing I didn't tell you is actually, maybe that's 2 slides forward. But one thing I didn't tell you is that, of course, we want to describe things over landscapes. That's the overall goal. We're taking extreme measures of simplification here, but we want to know, is frost cracking going to happen at some particular elevation in some location, or is it going to be more down lower or more up higher? Where do we expect the damage to be occurring? And it'll be controlled by the temperature profile, of course. But if I were to integrate all of the change in porosity that is predicted, when these are tiny porosity changes, over depth, then I get this number. I get a heave, a total heave that takes place, and that's that. And then if I was to say, well, how deep do I have to go to get halfway there, that's where these lines are plotted along here. So that's all that is. Yeah, I'm glad you asked. Well, you'll notice that where the cusps are most prominent are on the blue curve and the red curve, I would say. And the red one is much deeper than the blue one. And the blue one is a little bit colder than the red one, so it's kind of interesting. But it all comes from water transport. So water transport is showing up here as this weighting function inside the integral. And when delta t gets close to delta t sub c, this is 1. As delta t gets colder than that, in other words, as this gets bigger, this weighting function gets smaller. And so where the cusps are coming from are locations where you just get up close to -3 degrees, and then it turns around and goes back down, but that there is still a strong temperature gradient at -3 degrees at that location. So that's how these things develop. And maybe it would help to think about taking a time. -3 is the upper limit in this particular case. Yeah.
So this suggests that depending on the temperature, the boulders that freeze off have a different size.
Yeah, no, that would suggest that. Yeah, you're absolutely right. Good question. I don't know. I'll talk more about that, though, about the other factors that might play a role. But that would be an interesting observation, and it is one that has been looked for, let's say. Here, I'm just to analyze this a little bit further. Think about what happens at 2 different depths. I'm plotting now just the change in porosity that's predicted by the model over the course of a year, where the middle of winter is at 0 days here, and then we're in the middle of summer on either side. So just a sinusoidal temperature variation. That's at 0.5 meter's depth. This is at 1 meter depth. And so we're looking at lines through 0.5 meter and 1 meter in this case. And what do we see? Well, we see that if it's super cold, well, I should start where it's super warm. Okay, let's start at 5 degrees. Mean annual temperature of 5 degrees with a temperature swing of 10 degrees. I believe that's right. We're going to just pop down below this line for a little bit in the middle of the winter. So I said it right. So in the middle of the winter, we can grow some cracks. That's this line right here. If we make the temperature a little colder, then you can see that there's a lot of cracking that happens in the fall and a little bit in the spring. And it's colder still for some reason. There's a little bit in the fall, lots in the spring, and it just sort of goes like that. So that's the predictions of the model. There's all kinds of funny behavior. We can have cracks grow and then be smaller, but we're within the cracking window the whole time, so we're treating them as a little bit goofy because cracks aren't healing, but nevertheless, this is just a simple model. And I'm just satisfying this equation. I had to put the diffusion of heat in there again because I'm not going to end at the same place as I started at. That's my permeability model, and this is what I basically just said. So where the cracks are depends both on your depth and also what your climate is. That's the idea. So that's a feature. The total amount of heave depends upon the climate. So that's this lambda value. Really cold climates, it's always primed for cracking, but it never gets warm enough for any water to go anywhere, and so forth. Excuse me. Really cold climates are, oh, these are amplitude. I see, I confused myself a little bit. These are all, really cold climates are over here. Really warm climates are over here. The bigger the amplitude of the temperature cycle, the larger the temperature gradients are that need to drive the water transport. And so that's the general idea. This other thing just talks about how deep cracking sort of tends to take place. The mean annual temperature is relatively warm. The thermal wave doesn't penetrate very deeply. If it's really, really cold, you just can't transport anything because the temperature gradients are so low down at depth, and the permeability is small. So that student that had me get into this stuff wanted to do it for a particular study in this location down here, near where she was a graduate student and where I'm a professor. And she continued to go on, and she was interested in last glacial maximum conditions. This is the modern climate. This is the last glacial maximum. And the plot down at the bottom here is that lambda parameter. It's sort of the integrated predicted damage at a given location over the course of a year. And she helpfully put Denver and St. Louis and Atlanta and DC on here, which all wind up in this mean annual temperature amplitude space as being too warm for cracking today, but in the distant past, perhaps they may have cracked. And since she's a geomorphologist, she's interested in whether cracks that were created 20,000 years ago might play a role in allowing water to penetrate bedrock and so forth today. Okay, so that's the idea. Okay. All right. So that's the model, and we should confront a little bit of data, and we don't have good data, but we can look in the literature and see a few things. This is from Nepal, going up to 8 kilometers of elevation or more, with these measured mean annual air temperature following a lapse rate, and the measured temperature amplitudes going along here. There are hill slopes of different aspects. Clearly, solar radiation is important, and it's not included in any of the temperature solutions here. Clearly, lithology, I don't know what the initials stand for, but they're different kinds of rocks, is also important. And for what it's worth, they have these debris-free ice in these elevation bands, and then debris-covered ice in this elevation band. So you might hope that there was more frost cracking to dump rocks onto the debris covered stuff than the debris-free stuff. I would not put a lot of weight in this prediction because we're just guessing at the daily temperature swing. But this sort of this pattern that with these temperature conditions and whatever else we stuck into the model, we could justify that, yeah, there'd be a lot of cracking down at this elevation, not very much up here and not very much down there just because of the changes in temperature. Big grains of salt with this one, okay? This is some work from the Alps where there are these people, these permafrost scientists that are also climbers, and they seem to want to spend their time putting instruments on rock walls in places that you shouldn't go. And in this particular case, it wasn't so crazy. There's a nice refuge right here, I suppose, so you can spend some time there. But they put out a couple of acoustic sensors, and so just like that early or 90s experiment, except this one not in the natural laboratory, I should say, they're paying attention to where the acoustic activity is coming in. I should say that this is the time spent in each bin, I suppose, so it was around 0 degrees much of the time. I can't remember how long these experiments lasted for. It's a difficult field experiment because there's things falling down all over the place. There's avalanches, there's rock falls, and of course your acoustic emissions are going to be most sensitive to rocks that are close. They're not able to do the tomography to figure out exactly where everything is. But that's sort of the pattern they get. What I would say is that this is probably not frost cracking, for example, at plus 5 degrees. But some of this might be. You see that it does not fall off as you go to colder temperatures, but then there's very little time spent at these cold temperatures, so who knows. So you can learn some things from these kinds of studies. You know, I think that was what they were trying to come up with out of these, you know, little seismic signals here, to learn something about the distribution of sizes. They do have a broad distribution of crack sizes. It's not just one crack. But to be honest, it's been a while. I don't remember exactly what they figured out. I do remember what Laura did. Laura was one of my master's students who was intending to do something else and then just waiting for equipment. I tried to get her working on something. There was, I guess, a summer student, and she needed to supervise this summer student, and so she supervised the summer student to take little rock cores from the Eugene Formation, which runs along the Willamette River here. So this is the sandstone. This sandstone is very, very good for the people that run their SEM and other imaging equipment in the basement of a building that sits upon this sandstone, because it is so weak and crappy that it just damps out all the vibrations from the nearby traffic. So apparently, I can't remember what the name of the company is that makes the SEM, but they, up near Portland, but they actually ship their new instruments to that lab where they get much better results than they do in their own lab because of the crappiness of this rock. So crappy rock, that's just exactly what we wanted. We drilled these little cores, and we expected that, well, the idea was that if we put these cores into a glycol bath, isolated from the bath, but we put them in saturated, our hope was that if we froze them really, really quickly, that we would force all that water that would freeze later to move towards the center of the sample and blow up the center of the sample in some way. And if we froze them more slowly, that the outsides would crack first. That was our idea. And it didn't work. But what did work is that you can see bath temperature down here and elapsed time, and you see this nice behavior where nothing happened until you got cold enough. And then there was a big broad range here where it only took an hour or two for cracking to take place. And then if you made it colder still, then cracks either never happened or only occasionally happened. So that was the idea. Now, if you look at what the modeled temperature profiles are in these tiny little cores, the story doesn't hold up super well, because we wanted our frost damage index to depend on temperature gradient squared, and there was no temperature gradient after about 10 or 15 minutes in any of these cores. So that wasn't really quite part of the explanation, but actually I'm happy about that because that's more interesting. So things broke after an hour or so, was the fastest that they broke. And they did it while the entire system was isothermal. Another little detail, this is in Norway. It's, yeah.
So, do you have any interpretation?
I do. I'll get to it. Okay. I think it's, is it there? No. Ah, yeah, this is it. This is my interpretation. I think that a single crack is likely to idealize, and this is Justina's work is just showing a distribution of cracks. You can't really apply this model faithfully to a distribution of cracks, not that we haven't done it anyways. But I think that what happens is that the important thing is that if you have a distribution of cracks, you expect that the big cracks can grow at a lower stress intensity than the smaller cracks. I mean, basically, there should be a coarsening that takes place. And I don't think that you need liquid water to be available. I think that all you need is there needs to be pre-melted water. You need to lower the water pressure on your big crack to suck water away from the little crack. And I think that's what's happening in her samples. I think it's just taking some time for the water to be redistributed, and it's causing these cracks to grow. And it cannot be captured by this model. Perhaps a statistical approach is called for. I have some ideas about what to do, but I haven't done it. And I should also mention that with unsaturated conditions, of course you get cracking. I did a little bit on unsaturated conditions in trying to sort of work our way through that. My wife is a building scientist. She's interested in lots of different things, but in particular in this work that we collaborated on together, she was interested in various building wall types, particularly made of natural materials like stabilized rammed earth and stabilized earth blocks and so forth. But we've also got concrete and masonry up here. And unlike me, she actually cares about real weather, so she uses real weather files. And this is from Golden, Colorado, just a model of how the temperature at various depths within a stabilized rammed earth change over the course of a week or so. And also how the relative humidity changes and the temperature gradient over that same time period. The details don't matter. If it was saturated in my model with a single crack size, we would expect the damage patterns to look something like this, where this is that 1 week period that's shown up here. We did try we know that buildings are usually not saturated. And so we tried to, tease out behavior or hand wave behavior that might happen, arguing that the unsaturated behavior would sort of scale with the saturated behavior, but the idea is that water is going to infiltrate preferentially to the smallest cracks. The largest cracks are the ones that want to grow. And so if we think our characteristic crack size is what controls damage, that characteristic crack size has to be smaller if it's unsaturated. So that's the idea, and we also changed the permeability and so forth. So I wouldn't hang my hat on it, but that was our idea. All right, so that is all I have for you. So I get 20 minutes early. I should get a prize. We've talked about this, it's related to that, arguably to that too, and I would say to all of this as well. And I would happily take any questions or direct you to more literature.